Sample problem 16.9 introduces to the concept of drawing reaction energy diagrams and thinking about transition states. So part of the fourth skill that we need to know for chapter 16 is transition state theory. And that states that high energy species exist at the moment of an effective collision when reactants are converted to products. And again, we can use those to think about the energy changes as the reaction proceeds from reactants to products. And that's really what a reaction energy diagram is. And we talked about the concept of roller bowler and having balls kind of roll over an energy landscape and thinking about where they might end up. So this problem asks us to look at a key reaction that occurs in the upper atmosphere, which is the combination of ozone with an atom of oxygen to generate 2 molecules of molecular oxygen. And so they tell us that the activation energy for this forward process is 19 kilojoules and that the delta H for the reaction as written is minus 392 kilojoules. So again, this minus 392 tells us that this is an exothermic reaction. And exothermic reactions always have an energy of the reactants much greater than the energy of the products. So it asks us to draw a reaction energy diagram and then predict a structure for the transition state and calculate the activation energy for the reverse process. All right, so let's talk about some of the key parts here. When we're asked to draw a reaction energy diagram, what you need to draw is a plot that shows the reaction progress on the x-axis, and then we're going to have some unit of energy on the y-axis. And in this case, they're telling us enthalpy. So we're going to have enthalpy values here. So they tell us that the delta H of the reaction is minus 392 kilojoules. And so that reminds us again in an exothermic reaction that the products are going to be much lower in energy here than the reactants. So here's our reactants. We have O3 and O, and then we've got 2 O2 as our products. Exothermic reactions means we go downhill in energy so that the delta H is minus 392 kilojoules. Remember, anytime you're figuring out a delta, always take products minus reactants. And if we take a smaller energy value here and we subtract a larger energy value, that's going to give us a negative value here. So that's why delta H is negative. Another way conceptually to think about this is if you start with a certain energy value in your reactants and you come down here to a much lower energy value for your products, that excess energy has to go someplace, and for an exothermic reaction, it's going to be given off as heat. Okay, so when this reaction proceeds, it's not just like you start right here and you slide right downhill to your reactants. We do have, at the end of the day, a decrease in the energy as we go from products to reactants. But as we're learning about, in order to have an effective collision, you have to get up and over a certain barrier to get to the other side. And that's what our activation energy is. So again, I'm going to try to draw this a little bit to scale. If this is close to 400 kilojoules for the drop in energy between products to reactants, it's about 20 kilojoules to go up and over a barrier. So right about here, right, we can go up and over here, and then once our molecules get up and over that barrier, they can come down to the other side. So in our roller bowler analogy, right, if we started with molecules that were here, they'd have to have enough energy to get up over to the top of this hill. And again, they tell us that this activation energy for the forward process is 19 kilojoules. And then once they're up at the top of this hill, they do have 2 options. They can slide back down to reactants, but it's a much more favorable process to go way downhill in energy and become products here. So again, we know that this value is 19 kilojoules per mole. So there's 2 parts here that it's asking us. After we draw a reaction energy diagram that's consistent with the information that's provided, we have to show 2 things. The first thing that they want us to do in terms of a numerical thing is to calculate the activation energy for the reverse. So again, remember, activation energies are always the energy difference between a species that exists and then a species that doesn't exist, which we call the transition state. And it's always going to be the energy difference between a species that exists and a transition state immediately preceding it. So if we're going in this direction, this is a species that exists, our reactants. As we head towards the transition state, Again, that's the transition between these reactants and products. We have to go up a hill that's 19 kilojoules, okay? And then sliding down to the other side to products. So the forward, okay, activation energy for the forward or for the reverse direction is going to be this energy level. For the products, going in the reverse direction is going to be the same amount of energy then, or the amount of energy that it takes to get to that same transition state. So the question is how do we figure out what this value is? So again, if this is A and we call this B and this C, hopefully it makes sense that the value of C is going to be equal to A plus B. We have to get back up this hill to the same energy level here, but then we still have that little bit that we have to go over. So in this case, we're going to have the 19 plus the 392. So C is going to be equal to 19 plus 392, and that's 411. Make sure you don't use a negative 392 there because you won't get the right answer, but just conceptually think about this. We have to climb back up this hill, and the delta H value, we know that distance. So to get back up to this point on the hill is 392, and we know that this height is 19, so we have an additional 19 we have to get up and over. So in this case, the EA for the reverse process is going to be 411 kilojoules. Okay, the last part of this problem asks us to think about a structure for this transition state. And remember, the transition state really represents the kind of transition between a molecule of ozone and an atom of oxygen going to make two molecules of molecular oxygen. So as a little bit of a review here, let's think about what these structures look like, right? So if you're having a hard time figuring out how would I draw ozone, remember the first thing that you have to figure out is how many total electrons you're going to have in your system. And that is the total number of valence electrons that each atom contributes. So each oxygen atom is going to contribute 6 electrons. We've got 3 of them, so that's 18 electrons total. We know that our 3 oxygen atoms are going to be connected together. They're not going to be in a triangle shape because that's very strange, so there's a linear arrangement here. We always connect first with single or sigma bonds, and that takes up 4 electrons, right? 2 electrons here and 2 electrons here. What we can go around is put the rest of our electrons. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. Well, what we can see here is we've got an atom that has an incomplete octet. If you have atoms that have incomplete octets, it's probably because there's a neighboring atom that has a pair of electrons that they're supposed to be sharing, not having as a lone pair. So we can take and have these electrons come down and be shared with the adjacent atom. And what we'll see now is this makes, everybody happy because each atom has a complete octet. If you need to go back and review this from Gen Chem 1, make sure that you're able to do that so we can draw proper Lewis structures. This oxygen atom has 2, 4, 6, 8 electrons all around it. Same with this guy, 2, 4, 6, 8. Same with this guy, 2, 4, 6, 8. Everybody has 8 electrons around them, so they're happy. They have a complete octet. But each of these atoms is different. This atom over here has 2 lone pairs and is sharing electrons as 2 bonds. So the reality is it owns these 4 electrons and only shares half of these 4. So this atom only owns 6 electrons. This atom owns 7 electrons. And this atom owns 5 electrons. And that's a really important point to make sure that you understand. Each of these oxygen atoms has a complete octet around it. Everybody has 8 electrons around it. Because of ones that are lone pairs versus bonded electrons, it's going to make a difference for the formal charge. So this atom, again, owns 6 electrons. Because its valence number is 6, there's a 0 formal charge on this oxygen atom. This middle oxygen atom owns 5. It wants to own 6 electrons because of its valence. So it's 1 electron deficient of what it wants to own, which means it has a positive 1 charge. Don't get confused with formal charges. This doesn't mean it has one more electron than it wants. It means it's missing one electron, so it has a formal charge of +1. This last oxygen atom, it owns 7 electrons. It owns one more than it wants, which is 6, which means the formal charge is -1 on this oxygen atom. So ozone's kind of a complicated Lewis structure to draw, but we can see that the net charge, the overall charge on a molecule of ozone, is 0 because this +1 and this -1 cancel out. But these are real formal charges on this molecule, and that's really important because it lends to some of the reactivity we're going to see here. Okay, so here again is our ozone molecule. It's reacting with an oxygen atom. So an oxygen atom just comes in with its 6 electrons. We're going to make molecular oxygen, which again has this Lewis structure. So we need to think about, as we are transitioning between these two reactants and then 2 molecules of these product, what does that transition state look like? What does that look like on a molecular level? Well, hopefully we can look here and see that what's really happening is this is going to be a bond that's breaking, right? We can sort of see that there's one oxygen molecule that we're going to have. And so we need to form a new bond between this. So we need to form a bond between there. So if we think then about drawing what that transition state would look like, we can take this part of our ozone and we can show this as kind of a dash bond because that bond is breaking to this other oxygen atom. And then we're going to be, again, forming a bond over here. Okay, so we've got, again, the ability to break a bond here. So this is going to be breaking because this was our O3. And now we're forming a bond here. So again, bringing in a lot of parts of chemistry that we've already learned about in terms of drawing structures, thinking about that ozone is reactive because we have this unequal distribution of electrons, and that's going to allow us to do some bond breaking and bond forming, and thinking about what that actually looks like in a transition state species. And so just like a ball would not exist at the top of this hill, this molecule doesn't actually exist, but it shows us that we're going to be breaking a bond to this between this oxygen atom and the rest of the ozone, and forming a bond between this oxygen atom and that other oxygen atom from ozone.